Welcome to the deep dive. Ready to tackle some Ramsey theory?
Always up for a challenge.
Today we're looking at the L problem, and we've got a stack of research papers here
Oh, this should be good.
that really dig into it.
Yeah, the L problem, it's a classic example of how these deceptively simple rules can lead to some pretty complex outcomes.
Right, like you start with this idea of coloring a grid,
Yeah.
and then suddenly you're in this world of proofs and theorems. But we're going to break it all down, explore just how big a grid needs to be to guarantee finding a specific pattern, no matter how you color it.
It's like a treasure hunt through the world of mathematics.
I like that. A mathematical treasure hunt. Okay, so let's set the stage here. What exactly do we mean by a monochromatic L?
Well, imagine a grid like a checkerboard, right?
Okay.
Each square can be one of three colors. The L shape we're looking for is basically 3 points that form a right angle, like think of a Tetris L block.
Okay, I can picture that.
More formally, if we think of the grid with coordinates, like 11, 1, 1, 2, and so on, a monochromatic L would be formed by points, ij plus t, and I plus t, j plus t. All 3 points have to be the same color. The t there just means the arms of the L can be any length.
Right, as long as they keep that right angle shape.
Exactly.
And the notation for the smallest grid size that guarantees you'll find this monochromatic L using 3 colors is R3L, right?
Precisely. And before we jump into the really complex stuff, it's worth mentioning the simple cases, the trivial ones. With just one color, R1L is just 2.
Because a 2x2 grid, every point's the same color, so you're automatically going to have those L shapes everywhere.
Exactly. And with 2 colors, R2L is 5.
Meaning you can color a 4x4 grid with 2 colors and avoid making a monochromatic L.
Yeah, you can, but once you hit 5x5...
It's unavoidable.
Right, a 5x5 grid guarantees you'll find one.
Okay, so those are the easy wins. But with 3 colors, things get much more interesting, and that's where this first paper comes in.
Yeah, the one by Kanaki et al. They're trying to find an upper bound for R3L.
So basically, how big does the grid need to be before you're guaranteed to find that 3-color L?
Exactly. And their approach uses this really elegant idea called the pigeonhole principle.
Okay, remind me about the pigeonhole principle.
So it's pretty simple, really. If you have more pigeons than pigeonholes, at least one of those pigeonholes has to have more than one pigeon in it.
Right. Makes sense.
Kanaki et al. Apply this to our 3-colored NXN grid. They start by looking at the main diagonal, that line of squares going from the top left to the bottom right.
Okay, I'm following so far.
So we've got 3 colors and n squares on that diagonal. The pigeonhole principle tells us that there must be at least n3 points on that diagonal that are all the same color.
Okay, because we've got more squares than colors, so some squares have to share a color.
Exactly. Now, let's say, for argument's sake, that those points are red.
All right, so we've got some red points along the diagonal. What's next?
Now comes the clever part. Each pair of those red points actually forces a specific point below the diagonal to be either blue or green.
Why is that?
Because if that point were also red, we'd have a red L, right?
Ah, I see. So those points below the diagonal can't be red to avoid creating that red L.
Exactly. And the paper goes on to calculate the number of these forced blue-green points, and it turns out to be n3 choose 2.
Which basically represents all the different ways you can choose 2 of those red points on the diagonal.
Precisely.
Okay, so we have the diagonal with red points and a bunch of blue or green points below it. What happens next?
Well, those blue-green points are spread across n1 subdiagonals, those lines parallel to the main diagonal but below it. Naturally, one of those subdiagonals has to have a higher concentration of those blue-green points.
Okay, I'm with you.
Now they apply the pigeonhole principle again to this dense subdiagonal. Since those points can only be blue or green, at least half of them have to be the same color. Let's say, for argument's sake, that color is blue.
All right, so now we've got blue points coming into play.
Yeah, and just like before, each pair of those blue points forces a point even further below them to be a certain color.
To avoid creating another blue L.
Well, this time it's not just about avoiding a blue L. It can't be red either, remember, because it would create a red L with the original red points on the main diagonal.
Ah, right. So these new points, they have to be green. It's like a chain reaction.
Exactly. We start with red points, they force blue-green points, then the blue points force even more green points, and this eventually leads to a contradiction.
Because there's just not enough space on the grid to accommodate all these forced green points without creating the L shape we're trying to avoid.
Precisely. The grid isn't big enough. So the question becomes, what's the smallest n, the smallest grid size, where this contradiction happens?
Where we just can't avoid creating that monochromatic L.
Exactly. And the researchers found that that number, the The smallest n is 2593.
Wow, 2593. So any grid that size or bigger is guaranteed to have a three-color L no matter how you color it.
That's right. And that's how they establish that upper bound, R3L 2593.
That's pretty impressive. But I know we can do even better than that.
Oh yeah, this is just the beginning. The next paper we have takes things even further, refining that upper bound by looking at how these red points are arranged along the diagonal using this concept of intervals.
And intervals. Okay, now I'm really intrigued.
It's a clever approach, very clever. Think of an interval as the number of points between two of those red points on the diagonal.
So like if two red points are right next to each other, the interval is 0.
Exactly.
And if there's 1 point between them, the interval is 1.
You got it. We can label these intervals with I sub.
Where Tim is just the number of the interval.
Right. So a sub 1 sub would be the interval between the first and second red points, a sub 2 sub between the second and third, and so on. And each of these intervals, just like the red points themselves, force some points below the diagonal to be blue or green.
Because, again, if anything within that interval was red, it would create that red L shape.
Exactly. So what the authors of this paper realized was that the way these intervals are arranged on the diagonal, it really matters. They wanted to find the most space-efficient arrangement.
So like minimizing the total space taken up by the red points and the intervals between them?
Precisely. And they actually used a Python script to test out different interval arrangements, looking for the most space-efficient one.
Wow. Bringing some computational power into the mix.
It's a pretty cool approach.
So how does this script actually work?
Well, it starts with a small grid where we know we can avoid making a monochromatic L, and then it gradually increases the grid size. As it does that, it calculates the minimum space needed for each arrangement of those intervals.
And when that minimum space needed is bigger than the diagonal itself.
That's when we hit our contradiction. We know we found a new upper bound for R3L.
That's so clever. So what did they find? What's the new upper bound using this method?
They were able to bring it down from 2593 all the way to 1804.
Wow. Just by optimizing the intervals.
Yeah.
That's really impressive. But I remember you saying that they actually go even further than that in this paper.
We've only been talking about intervals between consecutive red points. This paper also considers intervals between red points that aren't next to each other.
So like, instead of just looking at the space between the first and second red points, we could look at the space between the first and third, the second and fifth, and so on.
Precisely. We can actually express those bigger intervals in terms of the smaller ones.
Like building blocks.
Exactly. The interval between the first and third red point, we'll call it a sub 1003 sub, would be equal to the sum of a sub 1 sub and a sub 2 sub plus 1 to account for the second red point itself.
I see. And adding these bigger intervals into the mix gives us even more flexibility in how we arrange things.
Right. And that leads to even tighter constraints, which brings the upper bound down even further.
Okay, drum roll, please. What's the new upper bound?
Down to 1573.
1573. It's amazing how much progress can be made just by carefully analyzing these intervals and how they force the placement of the other colors.
It really highlights the hidden structure within this seemingly simple problem, doesn't it?
It really does. We've been talking a lot about the upper bound, but what about the lower bound for R3L? What's the smallest grid size where we know we can avoid that monochromatic L?
Well, the research mentions that the current lower bound is 21. So someone has managed to color a 20 by 20 grid with 3 colors and avoid creating a monochromatic L.
That's pretty impressive, but they haven't been able to do it on a 21 by 21 grid.
Not yet. Apparently, it's proven to be incredibly difficult, even with advanced algorithms and a lot of computing power. The paper mentions attempts to improve the lower bound using SAT solvers.
SAT solvers.
They're really sophisticated computer programs that can test the satisfiability of logical statements.
So they translate this visual geometric problem into a logic problem that a computer can solve.
Precisely.
Fascinating. So the SAT solvers have been successful on a 20 by 20 grid, but not a 21 by 21.
That's right.
Okay, so we've got an upper bound of 1573 and a lower bound of 21. That's quite a gap. But you mentioned one more paper that throws a completely different tool into the mix, right?
Yeah, this last paper introduces the concept of Golomb rulers. They offer a whole new perspective on how we can analyze those forced blue points we were talking about earlier.
Golomb rulers. I'm not familiar with those at all.
They're really interesting mathematical objects. Essentially, a Golomb ruler is a set of integers where all the distances between any two elements are unique.
Can you give me an example? I'm having trouble picturing that.
Sure. Imagine a ruler with markings at positions 0, 1, 4, and 6. That would be a Golomb ruler because all the distances between those markings are different. 1, 3, 2, 5, and 4. No repeats.
Okay, I'm starting to see it. It's like a ruler with very specific markings so that every distance you can measure on it is unique. But how does this connect back to our L problem?
That's where it gets really interesting. Remember those blue points we were talking about? The ones forced below the diagonal to avoid the red L shapes? The researchers realized that if the positions of those blue points on a subdiagonal formed a Golomb ruler, it could actually prevent the formation of too many green points further down.
Wait, how does that work? How can a Golomb ruler prevent green points?
Let's visualize this. We've got a subdiagonal with those forced blue points, right? And remember, each pair of blue points forces a point below to be green to avoid making a blue L. But if those blue points are positioned according to a Golomb ruler, meaning all the distances between them are unique, then no two pairs of blue points will force the same green point below.
Ah, I see. It's like each pair of blue points gets its own designated green point. They're spread out, preventing those clusters of green points that could lead to a monochromatic L.
Exactly. And by incorporating this Golomb ruler concept, the researchers were able to set much stricter limits on the number of blue points allowed on a subdiagonal. And amazingly, this leads to a significant improvement in the upper bound for R3L.
Okay, I'm on the edge of my seat here. What's the new upper bound using these Golomb rulers?
It trucks all the way down to 493.
493. That's a huge improvement from 1573. I never would have guessed that something as abstract as a Golomb ruler could have such a big impact on this grid coloring problem.
It's pretty remarkable, isn't it? It really shows how interconnected different areas of mathematics can be.
So we've been on this incredible journey with the L problem. We started with the pigeonhole principle, explored interval optimization, and now we've encountered these fascinating Golomb rulers. We've managed to bring that upper bound down to 493, while the lower bound is still sitting at 21.
And despite all of these sophisticated techniques and computational power, the exact value of R3L remains a mystery, a challenge for future mathematicians to solve.
It's like we've peeled back the layers of the onion, but the core still holds some secrets. We've seen how the colors tend to cluster in grids that successfully avoid the monochromatic L, and how Golomb rulers seem to enforce a kind of spreading out of those colors.
It really makes you wonder if there's a deeper connection there. Could the properties of Golomb rulers somehow explain those clustering patterns? Is there some deeper structure governing how the colors need to be arranged to avoid that L shape?
Now, that's a fascinating question. Maybe one of our listeners will be the one to crack the code and finally determine that exact value of R3L.
It's a puzzle worth pondering for sure. And who knows what other mathematical treasures we might discover along the way.
Absolutely. Thanks for joining us on this deep dive into Ramsey theory and the L problem. Until next time, keep those minds curious and those grids colorful. Okay, you mentioned intervals.
Yeah.
How do those fit into all of this?
Well, this next paper dives deeper into the arrangement of those red points we were talking about, the ones on the main diagonal.
Right.
They introduced this concept of intervals to kind of refine the upper bound further.
Okay.
Think of an interval as the number of points between two red points on that diagonal.
So if I have two red points right next to each other, the interval is 0. And if there's one non-red point between them, the interval is 1.
Exactly. And we can denote these intervals as a sub-sub, where DE just labels the interval.
Okay.
So for example, a sub-1 sub would represent the number of points between the first and second red points, a sub-2 sub between the second and third, and so on. What's important is that each of these intervals, just like the red points themselves, forces some points below the diagonal to be either blue or green.
Right, because if any point within an interval were red, it would create a red L with the two red points that define that interval.
Precisely. So to avoid that, those points within the interval have got to be blue or green.
Yeah.
And what the authors of this paper recognized, very cleverly, I might add, was that the way these intervals are arranged on the diagonal is crucial.
Okay.
They wanted to find the most space-efficient arrangement, like minimizing the total space taken up by both the red points and the intervals.
So minimizing the overall footprint of those red points and the gaps between them.
Yeah, exactly. While still forcing enough blue and green points below the diagonal to guarantee that we eventually get that monochromatic L.
So it's this balancing act. We need enough of those forced points to create that contradiction, that unavoidable L shape.
Right.
But we also have to be careful about how those points are clustered on those subdiagonals.
Exactly. If you get too many blue or green points clustered together on a subdiagonal, you could trigger that monochromatic L too early before the grid is actually big enough to force it.
I see. So it's like a delicate dance.
It is. And this paper, they turned this balancing act into a really fascinating optimization problem.
Okay.
They actually used a Python script to test out different interval arrangements and to find the most space-efficient one.
Bringing in the computational power. I like it. So how does this script work?
It's pretty cool. The script starts with a small grid size where we know a monochromatic L can be avoided.
Right.
And then it gradually increases the grid size.
Okay.
And as it does that, it's calculating the minimum space required for each configuration of intervals. And as the grid grows, the script keeps checking if this minimum space required, the space for all the red points in their intervals, if it ever exceeds the length of the diagonal.
So when the minimum space needed for all those red points and their gaps surpasses the space available on the diagonal, that's when we know we've hit that contradiction.
Exactly. And at that point, we've found a new, smaller upper bound for R3L.
That makes sense. So what did the script reveal? What's this new upper bound?
Through this optimization process, they were able to lower the upper bound from 2593 down to 1804.
Wow, 1804. That's pretty significant just by optimizing those intervals. But I remember you saying that this paper goes even further, right?
We've only considered intervals between consecutive red points so far.
Oh.
The paper also explores intervals between red points that aren't next to each other.
So like instead of just the space between the first and second red points, we could consider the space between the first and third, the second and fifth, and so on.
Precisely. And we can actually express those larger intervals in terms of the smaller ones.
So we're basically combining those smaller consecutive intervals to form larger intervals spanning multiple red points.
Exactly.
It's like using building blocks.
Right. So the interval between the first and third red point, we can call it a sub 1003 sub.
Okay.
It would be equal to the sum of intervals, a sub 1 sub and a sub 2 sub, plus 1 to account for the second red point itself.
It's like we're building upon those smaller intervals to make bigger ones.
Absolutely. And incorporating these larger intervals leads to even tighter constraints, which helps to refine the upper bound even more.
I see. It's like each refinement gives us a more precise understanding of that upper limit.
Precisely. And the paper shows that this approach pushes the upper bound down to 1573.
Wow, 1573. It's amazing how much progress we can make by simply analyzing these intervals and how they force the placement of the other colors.
It really highlights how much structure is hidden within this seemingly simple problem.
It really does. Now, we've focused mainly on the upper bound so far. What about the lower bound for R3L? What's the smallest grid size where we know for sure that a monochromatic L can be avoided?
Well, the current lower bound, according to the research, is 21.
Okay.
Which means that someone, somewhere, has managed to color a 20 by 20 grid with 3 colors without creating a single monochromatic L.
That's pretty impressive.
Yeah.
But they haven't been able to do it on a 21 by 21 grid.
Not yet, it seems. The paper mentions attempts to improve that lower bound using what are called SAT solvers.
SAT solvers, what are those?
They're basically sophisticated computer programs that can test the satisfiability of logical statements.
Okay.
So essentially, they encode the rules of our L problem into a logical formula.
Ah, so they're translating this visual geometric problem into a logical problem that a computer can understand and work with.
Exactly.
Fascinating. And these SAT solvers have been successful on a 20 by 20 grid, but not a 21 by 21.
That's right. Even with powerful algorithms and parallel computing, finding a 21 by 21 grid without a monochromatic L has proven incredibly difficult.
It really shows just how complex this seemingly simple problem can be.
It does.
So we have an upper bound of 1573 and a lower bound of 21. That's quite a gap. But you mentioned one more paper that introduces a completely different approach, right?
Yes. This final paper you've provided explores an approach using something called Golomb rulers.
Golomb rule.
Yeah. And these Golomb rulers, they offer a whole new way to analyze those forced blue points we've been talking about. They might just hold the key to shrinking that gap between the upper and lower bounds.
Okay, now I'm really curious. Golomb rulers, huh? What are those and how do they tie into the L problem?
Well, they're a bit of a mathematical curiosity. Essentially, a Golomb ruler is a set of integers where all the distances between any two elements in the set are unique.
You give me an example. I'm having trouble visualizing that.
Sure. Imagine a ruler with markings at positions 0, 1, 4, and 6. Now that would be a Golomb ruler because all the distances between those markings are different. 1, 3, 2, 5, and 4. There are no repeated distances.
Okay, I'm starting to get it. It's like a ruler with very specific markings, chosen so that every distance you can measure on it is unique.
Exactly.
But how does this connect to the L problem? How do these Galam rulers come into play with coloring grids?
Well, this is where it gets really interesting. Remember those blue points we were talking about? The ones that are forced below the diagonal to avoid creating those red L shapes?
Right, yeah.
The researchers in this paper discovered something pretty amazing. They found that if the positions of those blue points on a subdiagonal form a Galam ruler, then it actually helps to prevent the formation of too many green points further down the grid.
Wait, how does that work? How can a Galam ruler prevent the formation of green points?
Let's try to visualize it. We have a subdiagonal, right, with those forced blue points on it. And each pair of blue points, remember, forces a point below them to be green to avoid making a blue L shape.
Right, I remember that part.
But if those blue points are positioned according to a Galam ruler,
Meaning all the distances between them are unique.
exactly, then no two pairs of blue points will force the same green point below them.
Ah, I see. So it's like each pair of blue points gets its own designated green point. They're spread out, so they don't create those dense clusters of green points that could eventually lead to a monochromatic L.
Precisely. That's the beauty of it. And by incorporating this Galam ruler concept, the researchers were able to establish much stricter limits on the number of blue points that are allowed on a given subdiagonal.
So they're using these Galam rulers to strategically spread out the blue points,
Yeah.
which in turn prevents the green points from clustering too much and triggering the formation of that monochromatic L too early.
Exactly. And this, surprisingly, leads to a significant improvement in the upper bound for R3L.
Okay, drum roll, please.
Yeah.
What's the new upper bound using these Galam rulers?
With the introduction of Galam rulers, the upper bound for R3L plummets to 493.
493. That's a massive improvement from 1573. I never would guess that such an abstract concept like these Galam rulers would have such a profound impact on this problem of coloring squares on a grid.
It's a testament to the interconnectedness of mathematics, really.
It is.
The seemingly simple problem of coloring squares can lead us to these really intricate concepts and reveal these hidden structures that govern how these colored points can be arranged.
Absolutely. So we've been on this fascinating journey exploring the L problem. We started with the pigeonhole principle, delved into interval optimization, and now we've encountered these intriguing Galam rulers. We've managed to bring that upper bound down to 493, while that lower bound remains at 21.
And despite all these sophisticated techniques, all this computational power, that exact value of R3L remains a mystery. It's a challenge for future mathematicians to crack.
It's like we've peeled back layers of the onion, but the core still holds some secrets. We've seen how the colors tend to cluster in grids that successfully avoid that monochromatic L, and we've seen how those Galam rulers kind of enforce a spreading out of the colors, preventing them from becoming too concentrated.
Right.
It makes you wonder if there's a deeper connection there.
Yeah, it does, doesn't it?
Could those properties of Galam rulers somehow explain those clustering patterns we've observed?
That's a great question.
Is there some deeper structure, some underlying principle that governs how the colors need to be arranged to avoid forming that L?
Definitely something to ponder.
Absolutely. And who knows, maybe one of our listeners will be the one to unravel that mystery and finally determine the exact value of R3L.
I hope so. It would be a remarkable achievement.
It would. Thanks for joining us on this deep dive into Ramsey theory and the L problem. Until next time, keep those minds curious and those grids colorful. Okay, so we've got this gap between the upper and lower bounds for R3L. And you mentioned these Galam rulers. What are those, and how do they relate to the L problem?
Galam rulers are fascinating mathematical objects. They're sets of integers where the distances between any two elements in the set are all unique.
Can you give me an example? I'm having a bit of trouble picturing that.
Sure. Imagine a ruler, but instead of the usual markings, it only has markings at positions 0, 1, 4, and 6.
Okay.
Now that would be a Galam ruler because all the distances between those markings are different. 1, 3, 2, 5, and 4. There are no repeated distances.
Okay, I see. So it's like a specially designed ruler where every measurement you can make on it is unique.
Exactly.
But how does this connect back to our L problem? How do Galam rulers help us with coloring grids?
This is where it gets really interesting. Remember those blue points we talked about? The ones that are forced below the diagonal to avoid creating those red L shapes?
Right, yeah.
Well, the researchers in this paper discovered that if the positions of those blue points on a subdiagonal happen to form a Galam ruler, then it can actually help to prevent the formation of too many green points further down the grid.
Wait, hold on. How does that work? How can a Galam ruler prevent green points?
Okay, let's try and visualize this. We have a subdiagonal, right? And it has those forced blue points on it. And remember, each pair of blue points forces a point below them to be green to avoid making a blue L shape.
Right.
But if those blue points are positioned according to a Golomb ruler, meaning all the distances between them are unique, then no two pairs of blue points will force the same green point below.
I get it. It's like each pair of blue points gets its own designated green point. And since they're all spread out according to the Golomb ruler, they don't create those dense clusters of green points that could eventually lead to a monochromatic L.
Exactly, you got it. And by using this Golomb ruler concept, the researchers were able to set much stricter limits on the number of blue points that are allowed on a subdiagonal.
So they're using the Golomb ruler to spread out those blue points in a very strategic way.
Right.
And that prevents the green points from bunching up too much and triggering the formation of that monochromatic L too early.
Precisely. And the amazing thing is, this technique leads to a huge improvement in the upper bound for R3L.
Okay, I'm ready for the big reveal. What's the new upper bound using these Golomb rulers?
With Golomb rulers in play, the upper bound for R3L plummets all the way down to 493.
493, that's incredible. From 1573 to 493, that's a massive improvement. I never would have thought that a concept like Golomb rulers could have such a significant impact on this grid coloring problem.
It really shows you how seemingly unrelated areas of math can sometimes have surprising connections.
It does. Okay, so we've been on this amazing journey exploring the L problem. We started with the pigeonhole principle, then we dug into interval optimization, and now we've discovered these fascinating Golomb rulers. We've managed to shrink that upper bound down to 493, while the lower bound is still at 21.
And even with all of these advanced techniques and all the computational power we can throw at it, that exact value of R3L still remains a mystery.
It really is a tantalizing puzzle, isn't it?
It is.
It's like we've peeled back some layers of the onion, but the core is still hiding some secrets.
Right.
We've seen how the colors tend to cluster in grids that manage to avoid that monochromatic L. And we've seen how Golomb rulers force a kind of spreading out of those colors, preventing them from getting too concentrated.
Yeah.
Makes you wonder if there's an even deeper connection there.
It does, doesn't it?
Could those properties of Golomb rulers actually explain those clustering patterns we've observed?
It's a great question.
Is there some deeper underlying structure that governs how those colors need to be arranged to avoid that L shape?
Definitely something to think about.
It is. Maybe one of our listeners out there will be the one to finally crack the code and figure out the exact value of R3L.
It would be quite a breakthrough.
It would. Well, thanks for joining us on this deep dive into Ramsey theory and the L problem. It's been a fascinating exploration. Until next time, keep those minds curious and those grids colorful. Welcome to the Deep Dive. Ready to explore some Ramsey theory?
Always up for a good mathematical challenge.
We're diving into what's known as the L problem today. Sounds simple enough, but I have a feeling it's going to get pretty complex.
Oh, it definitely does. It starts with a grid. Think like a giant checkerboard, right?
Okay, got the checkerboard.
And each square on that board, each point, you can color it. But you only get 3 different colors to work with.
All right, so I'm picturing this grid starting to fill it in with 3 colors, kind of randomly.
Yeah.
What's the problem? Where's the puzzle here?
The L problem asks, how big does this grid have to be? Like, how many squares across and down before, no matter how you color it?
Yeah.
You're absolutely guaranteed to find 3 points of the same color that make an L shape.
So it's not just about finding any L, it's about finding the smallest grid where an L has to exist no matter how hard you try to avoid it.
Exactly. Like, what's that tipping point where an L becomes unavoidable?
We got some research here by Mammel, Smith, and Yerger. Looks like they've made some progress towards figuring this out.
They have, and they're doing it by tackling the problem from both sides, trying to find the smallest possible grid where you have to have an L and the largest one where you might still be able to avoid it. So they're looking for upper and lower bounds.
Ah, squeezing the answer from both ends. Clever. So what have they found out so far?
Well, they build on some earlier work, which established that in a grid with a certain number of squares, specifically 2593.
2593, that's enormous.
It is. But in a grid that big, you're definitely going to find a monochromatic L. So that sets our initial upper bound. But of course, we want to make that number smaller, more manageable.
I can imagine. So how do they start chipping away at that huge number?
They start by focusing on the main diagonal of the grid.
You mean like if I draw a line straight from the top left corner to the bottom right?
Precisely. And they use a simple but powerful idea called the pigeonhole principle. Basically, if you've got more pigeons than pigeonholes, some pigeons have got to share a hole.
I remember that one. So if you've got enough points on that diagonal line
Yep.
and only 3 colors, some of those points have to be the same color, just like pigeons crowding into holes.
Exactly. And to simplify things, they assume the most common color on that diagonal is red.
Makes sense. So I've got this diagonal with a bunch of red points on it.
Yeah.
How does that lead us to finding L shapes?
Here's the clever part. They realize that for every pair of red points on that diagonal, there's one specific point below the diagonal that would make an L shape with those 2 reds.
Okay. I see that, like completing the corner of the L.
Right. Now, if that third point were also red, boom, we'd have our monochromatic L.
So to avoid creating a red L, that third point, that corner point, it can't be red. It's got to be any of the other 2 colors.
Exactly. So now we've got some restrictions on how we can color those points below the diagonal.
Okay, so some points have to be certain colors to prevent those red L's. Where do we go from there?
The researchers start looking at the lines of points that run parallel to that main diagonal but shifted down, the subdiagonals.
Okay, picturing those lines running below the main diagonal.
What they realize is if you have enough of those forced points, those non-red points, clustered on a single subdiagonal, you're bound to have a pair that would create a monochromatic L with a red point on the main diagonal.
I get it. So if I have, let's say, a bunch of blue points clustered on one of those subdiagonal lines, there's going to be a pair of blue points down there that can team up with the red point up on the main diagonal to make a blue L.
Precisely. And by carefully analyzing how many of these forced points you can fit on a subdiagonal without creating an L, they prove that if your grid is 2,593 squares or bigger, it's just impossible to color it without making a monochromatic L somewhere. So that's our upper bound, at least for now.
That's pretty impressive reasoning. But I'm guessing they don't stop there, right? 2,593 still feels pretty big.
No, they've got more tricks up their sleeves.
Yeah.
Next, they introduced this concept of intervals on that main diagonal.
Intervals? Sounds musical. What do they mean by that?
It's simpler than it sounds. An interval is just the number of spaces between 2 red points on that main diagonal line.
Okay, so like if I have a red point, then 3 empty spaces, then another red point, that's an interval of 3.
Exactly. And they use these intervals to come up with a much smaller upper bound, 1804. That's a big improvement.
Wow, so they shrink it by almost 1,000 just by looking at the spacing between those red points. How does that work, mathematically speaking?
They create a formula that calculates the minimum amount of space you need on that diagonal to fit all the red points in the intervals between them.
So even if you squish those red points as close together as possible,
Right.
you still can't fit everything onto a diagonal that's smaller than 1804.
Exactly. They even wrote a Python script to help them calculate this, but the underlying logic is all about how those intervals have to work on that diagonal line.
That's so cool how they combine the math with a bit of coding to solve this. It's like a high-tech approach to this very abstract problem.
It is, and it shows how powerful these different approaches can be when you combine them. But wait, there's more. They then realized that they haven't even squeezed all the juice out of this interval idea yet.
Really?
Yeah.
What else can you do with intervals?
Well, up to this point, they've only been considering intervals between red points that are right next to each other on the diagonal.
Okay, yeah, like those little gaps between neighbors.
What if you looked at the intervals between all the red points, no matter how far apart they are?
Oh, interesting. So not just the little gaps, but like if I have a red point way over here and another one way over there, I look at that big gap too.
Exactly. And just by shifting their perspective like that, they managed to shrink that upper bound even further, down to 1573.
Wow, 1573. So by looking at the bigger picture, the intervals between all the reds, they get an even tighter squeeze.
That's amazing.
What's the math behind that new number?
They essentially come up with a new formula that takes into account all those possible intervals, not just the little ones between neighbors. And again, they use their Python script to crunch the numbers and find that new upper bound.
So the closer they look, the more patterns they find, and the smaller they can make that upper bound. What's the next big leap they make in their research?
This is where things get really interesting. They bring in a completely different concept that seems to have nothing to do with grids or colors. Golomb rulers.
Golomb rulers. So that's a new one. What in the world are those, and how do they relate to the L problem?
A Golomb ruler is basically a ruler where the markings are placed so that no two pairs of markings are the same distance apart.
Okay, I think I'm getting that. So like if I had a ruler with markings at say 0, 1, and 4,
Yep.
that would be a Golomb ruler because the distances between the markings are all different, 1, 3, and 4.
Exactly. Every pair of markings has its own unique distance. Now, how does this relate to the L problem? You got to think back to those forced points below the diagonal, the ones that can't be read.
Okay, those points that complete the L shapes, and they can only be one of the other two colors? I'm with you so far.
The researchers realized that those points on any given subdiagonal line have to be arranged like the markings on a Golomb ruler if you want to avoid creating a monochromatic L.
Ooh, wait, what? That doesn't seem obvious at all. Explain it to me like I'm 5, if you can.
All right. Picture one of those subdiagonal lines. Let's say all the forced points on that line have got to be blue. Each of those blue points is like a marking on our imaginary Golomb ruler.
Okay, got the blue points as markings.
The distance between those blue points represents the distance between the markings on the ruler.
All right, but why do they have to form a Golomb ruler? I'm still not seeing it.
Because if you have two pairs of blue points that are the same distance apart on that line,
Yeah.
you're inevitably going to create a monochromatic L shape no matter what.
Really? Walk me through that, because I'm not quite seeing it.
Okay, imagine you've got two blue points, we'll call them B1 and B2, and they're some distance apart on that subdiagonal. Then you've got two other blue points, B3 and B4, same line, and they're the same distance apart as B1 and B2.
So we've got two pairs of blue points, equal distances, all on that same diagonal line.
Right. Now remember those red points up on the main diagonal? Let's say there's a red point R1 that's in just the right spot to make an L shape with B1 and B2.
Okay, so R1 is like the corner of that L.
Exactly. Now because B3 and B4 are the same distance apart as B1 and B2,
Yeah.
there's got to be another red point, R2, up on the main diagonal that lines up perfectly to make an L with them.
I see it now. Because those distances are the same, the red points up on the main diagonal are forced to be in just the right positions to create two potential L shapes.
Exactly. And here's the problem. The point where those two L shapes would intersect, the point that would complete both of them, has to be a different color to avoid making a monochromatic L.
So to prevent that, the arrangement of the blue points on the subdiagonal line has to be like a Golomb ruler, where no two distances between points are the same.
You got it. It's incredibly clever. And by applying this Golomb ruler logic, they managed to shrink that upper bound all the way down to 493.
493, that's a huge jump from 1573. So we've gone from thousands down to just a few hundred for the upper bound. That's amazing progress.
It is. And it's a fantastic example of how a seemingly unrelated mathematical concept can suddenly become crucial for solving a problem.
It shows you never know where inspiration might come from in math. So we've talked a lot about shrinking that upper bound, but what about the lower bound?
That's a great question, and that's where we're headed next.
So we know that any grid bigger than 493 squares is guaranteed to have one of those monochromatic Ls. But now the question is, how small can we make the grid and still have that guarantee? What's that lower bound?
Right, we've shrunk the upper bound, but now the challenge is to push up the lower bound. And to do that, the researchers turned to some serious computational firepower, SAT solvers.
SAT solvers, I've heard of those. They're like those programs that can solve really complex logic puzzles, right?
Exactly. And they're perfect for problems like this, where you've got a bunch of rules, constraints, and you need to see if there's any possible solution that fits all of them.
So in this case, the L problem, our constraints are that every point on the grid has to be one of those three colors.
Yep.
And there can't be any monochromatic L shapes.
Right. So the researchers basically feed those rules into the SAT solver and say, okay, can you find me any grids that fit this description? Any grids that follow these rules?
Clever. So what did the SAT solver come up with?
Well, it managed to find a 20 by 20 grid, so 400 squares total, that didn't have any monochromatic Ls.
Interesting. So that means the lower bound has to be at least 21, right? Because if a 20 by 20 grid is possible without an L, then the smallest grid that must have an L has to be at least one bigger.
Exactly. They tried to get the SAT solver to find a 21 by 21 grid that worked, but no luck. So for now, the lower bound sits at 21. But that doesn't mean someone couldn't come along and find a way to push it up even higher.
It's like we've narrowed down the possibilities. We know the answer for that smallest grid size, that R3L value, has got to be somewhere between 21 and 493.
Precisely. But even though they couldn't nail down that lower bound exactly, the researchers did notice some interesting patterns in those grids that managed to avoid those monochromatic Ls.
Oh, what kind of patterns?
One of the things they observed was that the colors tend to cluster along the reverse diagonals of the grid.
Reverse diagonals, you mean like the lines that go from the bottom left corner up to the top right?
Exactly. It's almost like those reverse diagonals want to be dominated by a single color in the grids that actually work.
That's interesting. Is there any mathematical explanation for why that might be? Or is it just a coincidence?
Well, that's what the researchers are trying to figure out. They explore this observation by connecting it to something called van der Waerden numbers.
Van der Waerden numbers. I vaguely remember hearing about those in a number theory class once. They're related to those arithmetic progressions, right?
You got it. An arithmetic progression is just a sequence of numbers where the difference between each number is constant, like 2, 4, 6, 8. Each number is 2 bigger than the one before it.
Right. Each number increases by the same amount.
Now, van der Waerden's theorem states that if you color the natural numbers, 1, 2, 3, and so on, using a finite number of colors, you're guaranteed to find an arithmetic progression of a certain length where all the numbers have the same color.
So no matter how cleverly I try to color those numbers, if I'm only using, say, 3 colors, I'm bound to create an arithmetic progression, a sequence, where all the numbers are the same color.
Exactly. It's inevitable. And van der Waerden numbers tell you, for a given number of colors and a given length of progression, how many numbers you need to color before you're guaranteed to have that monochromatic progression.
Okay, it's all coming back to me now. It's like a mathematical guarantee. But how does this connect back to the L problem and those reverse diagonals? Not seeing the link.
Well, think about it this way. If you color each of those reverse diagonals with just one color, so the whole diagonal is one solid color, and you manage to do that without creating any monochromatic L shapes, then the way you assigned those colors, that sequence of colors, can't contain an arithmetic progression of length 3.
Wait, really? I'm not quite seeing why that has to be true.
Okay, let's imagine we number those reverse diagonals, starting with 1 for the shortest one up in the top right corner and increasing as we move down.
Okay, I'm picturing those diagonals with numbers on them, like a slanted coordinate system.
Now, let's say you color those diagonals using our 3 colors, and you do it in a way that doesn't create a single monochromatic L. The researchers are saying that the order you use to assign those colors, that sequence, can't have any 3 numbers that are all the same color and form an arithmetic progression.
Okay, but what happens if there is an arithmetic progression of colors? Help me understand why that would be a problem.
Let's say, just as an example, that diagonals 2, 5, and 8 all end up being colored blue. What does that tell us about the points on those diagonals?
Well, it means that all the points on diagonal 2 are blue, all the points on diagonal 5 are blue, and all the points on diagonal 8 are blue, right?
Exactly.
Yeah.
Now, picture a single point on diagonal 2. To make an L shape with that point, we need one other point on the same horizontal line and one other point on the same vertical line.
Right. That's how you make an L shape.
And because of how those diagonals are arranged, if you've got a point on diagonal 2, the points that would complete an L shape with it have to lie on diagonals 5 and 8.
Ah, I see it now.
Yeah.
If those 3 diagonals, 2, 5, and 8, are all the same color, in this case blue, then any blue point on diagonal 2 is automatically going to have 2 other blue points on diagonals 5 and 8 that can complete a blue L shape. It's unavoidable.
Precisely. So if you want to color those diagonals without creating any monochromatic Ls, you can't have any sequence of 3 colors that forms an arithmetic progression.
Wow, that's a really cool connection. I wouldn't have guessed that van der Waerden numbers would be lurking behind this L problem. It's like there's this deeper structure to how the colors have to be arranged if you want to avoid those L shapes.
Exactly. And even though this connection doesn't immediately tell us what the lower bound is, it does give us a whole new way of thinking about the problem.
It's like a new tool in our toolbox, a new lens through which we can examine the problem. So apart from those SAT solvers, what were some of the other approaches they tried to find, that 21 by 21 grid, the one that would prove the lower bound?
They explored a few different avenues. One of them was this idea of triangulation. Instead of trying to solve the whole 21 by 21 grid at once, they focused on creating a 21 by 21 right triangle that didn't have any monochromatic Ls.
A right triangle, so like cutting the square in half along the diagonal.
That's it. Their thought was, maybe if they could find a triangle that worked, they could somehow extend it to make a full square.
Did they have any luck with that approach?
They did manage to find some right triangles that could be colored without creating a monochromatic L, but when they tried to extend those triangles to a full square, The SAT solver said, nope, impossible.
So close, yet so far. It's like finding a piece of a puzzle but then realizing it doesn't actually fit. Frustrating.
Very much so. They also tried some other techniques, like fixing the colors of certain columns or diagonals in the grid to see if that helped the SAT solver find a solution faster.
So they were trying to use those patterns they observed, like the color clustering on the reverse diagonals, to give the SAT solver a little nudge in the right direction.
Exactly. For example, in that 20 by 20 grid that worked, they noticed that the rightmost column had a lot of blue points.
Okay.
So they thought, maybe if we force the rightmost column of a bigger grid to be all blue, that'll help the SAT solver find a solution.
Interesting idea. Did it work?
It did for smaller grids, like 18 by 18 and 19 by 19, but it actually took the SAT solver longer to find those solutions compared to just letting it run without any restrictions.
Oh, so it backfired a bit.
Yeah, and when they tried it with the 20 by 20 grid, it actually slowed things down even more.
So it's like a double-edged sword. Restricting some of the possibilities can sometimes make things more complicated for the SAT solver.
Precisely. And they had similar experiences when they tried fixing the colors along those reverse diagonals. They even tried fixing an entire diagonal to be one color, hoping it would simplify things. But the SAT solver told them it was impossible to avoid a monochromatic L with that restriction.
So those patterns are definitely interesting and suggestive, but it seems like trying to force them onto a larger grid doesn't always pan out the way you'd expect.
That's the challenge with these problems. They can be very sensitive to small changes, and what works for one grid size might not work for another. But even those failed attempts give us valuable information.
They help us rule out certain possibilities and narrow down the search space, right?
Exactly. They refine our intuition about the problem and guide us toward more promising avenues of exploration.
It's like every dead end we hit gives us a little more knowledge about the territory we're exploring.
Well said. So even though we still don't have a definitive answer for the lower bound of R3L,
Yeah.
we've learned a lot about the problem along the way.
We've seen how the arrangement of those points on the diagonals plays a crucial role, how Golem rulers can unexpectedly provide insights, and how computational tools like SAT solvers can help us explore the vast space of possibilities.
And let's not forget those tantalizing clues, like the color clustering on the reverse diagonals and the connection to van der Waals numbers. It's those open questions that keep mathematicians coming back for more. There's always something new to discover.
It really is remarkable how something that seems so simple on the surface, like coloring squares on a grid, can lead to such deep mathematical concepts.
It is, isn't it? It just goes to show you how interconnected different areas of math really are. We started with this geometry problem, and now we're talking about number theory, combinatorics, even a bit of computational complexity. It's amazing.
It's like all these different branches of math are woven together like threads in a tapestry. You pull on one thread, and it leads you to unexpected places.
I love that analogy. And this L problem research is a perfect example of that. You never know where exploration will lead you.
So let's take a step back and recap what we've learned about this L problem. We started with this huge upper bound, 2593, and through some clever analysis, we saw how the researchers managed to shrink that down to just 493. That's pretty impressive.
It is, and along the way we explored how the arrangement of points on those diagonals, both the main diagonal and those subdiagonals, plays a crucial role in whether or not you can create those monochromatic L shapes.
We even went on a detour into the world of Golem rulers. Who knew those would be relevant to this problem? But it turned out they were key to shrinking that upper bound even further.
Exactly. And of course, we couldn't leave out the computational side of things. SAT solvers proved to be invaluable tools for exploring different possibilities and pushing the boundaries of what we know about the lower bound.
And even though that exact lower bound remains a mystery, we did uncover some really interesting clues along the way, like the tendency for colors to cluster on those reverse diagonals.
Right.
And that unexpected connection to van der Waals numbers. Those were really mind-blowing moments.
They were, and I think those open questions are what makes this whole research area so captivating. There's still so much to discover, so many avenues to explore.
Speaking of open questions, there was one observation in the research paper that really caught my eye. The researchers hinted at a possible connection between those reverse diagonals and the lower bound of R3L, but they didn't go into a lot of detail.
Ah, yes. That's a really fascinating idea. It has to do with the way those colors are arranged on those reverse diagonals and how that arrangement might be the key to understanding why we need a certain size grid to guarantee those monochromatic Ls.
Can you elaborate on that a bit? I'm curious to hear more about how those reverse diagonals might influence the overall size of the grid.
Sure. Remember how we talked about those colors on the reverse diagonals not being able to form arithmetic progressions of length 3?
Right, because if they do, you automatically end up with a monochromatic L.
Exactly. Now, the researchers suggest that to avoid those problematic arithmetic progressions, the arrangement of colors on those reverse diagonals might need to have a certain level of, what's the word? Irregularity or maybe unpredictability.
Irregularity, unpredictability. Okay, I'm intrigued, but I need a bit more explanation. What do they mean by irregularity in this context?
Well, imagine you're trying to create a sequence of colors where no 3 colors in a row form an arithmetic progression. You can't have any obvious patterns, any repeating sequences. You don't want red, blue, green, and so on. You want to mix things up.
So it's like you're trying to make that color sequence as random or chaotic as possible?
Exactly. And they think that this need for randomness or irregularity in the arrangement of colors on those reverse diagonals
Yeah.
might be directly connected to how big the grid needs to be to guarantee that you'll find a monochromatic L shape.
Okay, I'm following the idea of avoiding patterns and trying to make things random, but I'm still not quite seeing how that relates to the overall size of the grid.
Yeah.
How does the arrangement of colors on a few diagonal lines determine whether we need a grid that's 20 by 20 or 100 by 100 to force an L?
That's a great question, and to be honest, it's still an open problem. Researchers are still trying to unravel that connection. But here's one way to think about it. Imagine you've got a grid where the colors on those reverse diagonals are arranged in a very regular, predictable pattern.
Okay.
It might be easier to find a way to exploit those patterns, to find a way to force a monochromatic L to appear.
Ah, I see. So if the colors are arranged in a way that's easy to predict, then you wouldn't need as big of a grid to guarantee finding a monochromatic L.
Exactly. But if those colors are arranged in a more random, unpredictable way, then it becomes much harder to find those patterns that would force an L. You might need a much bigger grid to guarantee that those L shapes will eventually emerge, just because it's so much harder to avoid them when the colors are all jumbled up.
So the more random or chaotic the arrangement of colors, the bigger the grid needs to be to guarantee an L. That's a fascinating idea. It's like introducing randomness into the problem inherently makes it more difficult.
It does, and it highlights the deep connections between seemingly disparate areas of mathematics. We've got geometry, number theory, and even a bit of chaos theory all mixed up in this one problem. It's amazing.
It really is. It shows you how math is constantly surprising us with these unexpected connections and insights. It's like we're peering into the structure of the universe and discovering these beautiful patterns and relationships that govern how everything works.
Yeah.
It's truly awe-inspiring.
I couldn't agree more. It's important to remember, though, this idea about the connection between reverse diagonal irregularity and the lower bound, it's still just a hypothesis at this point. It hasn't been definitively proven, but it opens up this whole new avenue for exploration, a new direction for research.
It's like they've shined a spotlight on this previously unexplored corner of the mathematical world, and now it's up to mathematicians to delve into that uncharted territory and see what treasures they can uncover.
Exactly. And that's what makes this research so exciting. It's not just about finding a specific number, a definitive answer for that lower bound. It's about broadening our understanding, uncovering new connections, and developing new tools and techniques that can be applied to other problems in Ramsey theory and maybe even beyond.
Well, as we wrap up our deep dive into the L problem today, I'm left with a sense of wonder and excitement. We've seen the power of human ingenuity, the beauty of interconnected ideas, and the allure of unsolved mysteries. The quest to find the exact lower bound of R3L continues, and who knows what other surprises and insights await us along the way. Maybe, just maybe, one of our listeners will be the one to finally crack this problem wide open. Until next time, keep exploring, keep asking questions, and never stop marveling at the beauty and mystery of mathematics. Welcome to the Deep Dive. Ready to tackle some serious combinatorial brain twisters? Today, we're diving into the L problem in Ramsey theory. We got some seriously hardcore research on this, so let's try to untangle it all.
Yeah, it's amazing how a question that seems so straightforward, like how big does a grid need to be to guarantee a specific shape, can lead to some seriously deep, complicated math.
I know, right? It's kind of like that game Connect 4, but instead of, trying to win, you're trying to make sure any player has to make a certain L shape, regardless of what colors they use.
And the real kicker here is we're talking about 3 colors, and well, that's where things get really interesting and really complex.
Okay, so for this deep dive, we've got a few different papers here. One from Kanecki, Christensen, Fleischman, McNabb, and Smoliat from 2023. Another one by the same authors, but it's from 2022. And then we have 2 more papers, this time from Guillaume from 74 and 75. All of these are like laser focused on this L problem.
Yeah, and they take us on a journey, starting from some basic counting principles all the way to some really advanced heavy-duty computational techniques, all with the goal of finding what's called R3L, which is the smallest grid size where no matter how you color it with 3 colors, you're guaranteed to have a monochromatic L shape.
And just as a quick reminder, we know R1L, that's 2, and R2L is 5, but R3L, that's been a real head scratcher.
Absolutely. So this 2023 Kanecki et al. Paper, they start by establishing an upper bound. They prove that R3L is less than or equal to 2593.
Whoa, whoa, whoa. That's a huge number. Like, how do you even begin to figure that out?
Well, they use a proof by contradiction, which leverages something called the pigeonhole principle. So imagine this massive grid, 2593 by 2593, and let's focus on the main diagonal.
Okay, so I'm picturing that line of squares running from the top left corner all the way to the bottom right corner.
Exactly. Now, since we have 3 colors and we have that many points along the diagonal, the pigeonhole principle tells us that at least 865 of those points have to be the same color. Let's just say, for the sake of argument, they're red.
Okay, so we've got this like line of red points all in a row. What happens next?
Here's where it gets pretty clever. Every single pair of those red points, right? Every pair of those red points actually forces a point that's below the diagonal to be either blue or green. Because if that point below was also red, then we'd have a red L.
Oh, right, because that point below the diagonal, if it were red, it would like complete the L shape with those 2 red points above it.
Exactly. And because we have so many red points on that diagonal, we end up with a ton of these blue and green points, these what we call forced points that lie along these subdiagonal.
Subdiagonal.
Yeah, think of them as like diagonal lines that are parallel to the main diagonal, but they're shifted downwards.
Got it. So it's like these forced points start to create their own patterns, right?
Precisely. And that's where the real magic happens.
Right.
So we're going to apply that pigeonhole principle again. With enough of these forced blue or green points, we're guaranteed to have a long stretch of the same color, let's say blue, along a subdiagonal.
So we have all these blue points all lined up diagonally. Does that like force even more points?
You got it. Every pair of those blue points now forces points even further down, right? Even further below them to be green. Because again, we don't want to create a blue L shape. So it's like this cascade, right? Forcing more and more points as we go down.
It's like a chain reaction of forced choices that all started with those red points on the main diagonal.
That's exactly right. And eventually, we run into a problem, a contradiction. We end up with more of these forced green points than we have spaces on the subdiagonals below. So our initial assumption that we could color the grid without creating a monochromatic L, that has to be false.
So it's like we're proving that something must exist by showing that it's impossible for it not to exist?
Yeah, that's a great way to put it. And that's how they established this upper bound, 2593. But the research didn't stop there.
Yeah, I bet those other papers we have, I bet they dive into how they refine that bound even further, right? It seems like 2593 is just the starting point.
You're absolutely right. And to go further, they have to get even more specific, more precise about how these forced points are arranged. And that's where the idea of intervals comes in.
Intervals. Okay, now I'm really intrigued. We'll have to say that for next time, though. But before we go, I'm just curious, what's the thing that stood out to you most about this initial proof?
I think what really fascinates me is how they took this problem that's very visual, very geometric, right? Finding this L shape, and they turn it into this pure logic puzzle using the pigeonhole principle. It's a beautiful example of how different parts of mathematics can all come together to solve a problem.
Okay, so last time we were talking about this, like wild proof that in a 2593 by 2593 grid, you're always going to have at least one of those L shapes that's all the same color if you're using 3 colors. And now we're we're going to get into these intervals. I'm not quite sure I'm picturing how they fit into all of this.
Right. Yeah. Intervals. Intervals are like the key to really pushing that upper bound, that 2593, even lower. You remember how we were talking about those red points in the diagonal and how they force the points below them to be either blue or green?
Yeah, it was like a chain reaction, right?
Exactly. Now we're gonna shift our focus a little. We're not just thinking about the red points themselves, but the spaces in between them. Right? The spaces between them on the diagonal, and those are our intervals.
Okay, so like if you have two red points and they're right next to each other, that's a really short interval. But if they're spread out, then the interval's a lot longer.
Yeah, exactly. And the thing about the length of the interval, it tells us something super important. It tells us which subdiagonal that forced point is going to land on. Like a short interval means the forced point is going to be closer to the main diagonal, right? But if the interval is longer, that forced point is going to be further down.
So it's not just about like how many force points we have, but also where they are, like how they're spread out on those subdiagonals.
Exactly. So here's the strategy. We want to find a way to arrange the red points and their intervals in a way that uses up the least amount of space. Like we're trying to pack them in as tightly as possible.
Okay, so like we're playing Tetris with red points and intervals.
Yeah, kind of. Like imagine you're packing a suitcase and you want to fit in as much as possible. So if we can show that even if we pack everything perfectly, as tightly as possible, and that minimum amount of space is still more than the length of the diagonal, well, we've hit a contradiction.
Because then like those red points literally can't fit without causing a monochromatic L to pop up somewhere, right?
Exactly. So to test this out, the researchers, they used a Python script, a computer program, to basically play this packing game with different grid sizes. They tried all kinds of different arrangements of red points and intervals.
So Python is doing all the grunt work here, testing out configurations that would take us like forever to do by hand.
Oh, yeah, for sure. And what they found was that for any grid smaller than 1804 by 1804, you could always find a way to arrange things so that you don't get too many forced points of the same color bunched up on a single subdiagonal.
But once you hit that 1804 mark, the game changes, huh?
Exactly. At that size, even with the absolute best packing strategy, you just run out of room. So that means R3L has to be less than or equal to 1804.
Wow, that's like they shaved off, what, over 700 from that initial bound just by like carefully looking at these intervals?
Yeah, pretty impressive, right. But the 2023 paper, they actually take it a step further. They realized that up until this point, they were only looking at intervals between red points that were like right next to each other.
Okay, so like the gap between the first red point and the second, then the second and the third, and so on.
Right, exactly. But what about like the gap between the first red point and the fourth one, or the second and the fifth? Those longer gaps, those non-consecutive intervals. Once you start factoring those in, it opens up a whole new level of strategy.
So it's like we unlocked like a secret level in our packing game, more possibilities to play around with.
Exactly. And by being really careful about how they accounted for these longer intervals, they were able to lower that bound even further, down to 1573.
That's amazing. But I got to imagine that keeping track of all these different intervals, like the different types and lengths, it must get super complicated, right?
Yeah.
Did they talk about how they dealt with that at all?
Yeah, they actually point that out as a major challenge. They call it interval sequencing, which is basically, it's the problem of finding the best possible order to arrange those intervals on the diagonal so you use the least amount of space.
So it's like a whole other puzzle on top of the original puzzle.
Pretty much. You've got all these different sized intervals, and you got to figure out how to fit them together in the most efficient way possible.
This is crazy. We started with a simple L shape, and now we're talking about interval packing and sequencing. It's mind-blowing.
Huh.
So where do we go from here?
Well, the 2023 paper, they introduced this really cool tool. It's called Golem rulers. Golem rulers, they have these unique properties that help to put some limits on how those forced points can be arranged. And that leads to some even tighter bounds.
Golem rulers. That sounds like straight out of geometry class. All right, I'm ready for the next level. Hit me with it. Okay, lay it on me. What are these Golem rulers all about? We've gone from like counting pigeons to packing intervals, and now we're bringing rulers into the mix. This is getting pretty wild.
I know, right? It might seem a little out there, but these Golem rulers, they actually fit perfectly into this problem. They help us deal with that challenge of how those forced points are arranged, especially when we're looking at those longer intervals.
Okay, so back up for a sec. What is a Golem ruler? Am I picturing like some ancient measuring stick with, like, magical powers or something.
Well, not exactly ancient, but they do have a certain elegance to them. Imagine, like, you have a ruler, right? But instead of all the markings being evenly spaced, they're placed so that the distance between any two markings at all, is unique. No two distances are the same.
So it's kind of like a ruler that's made for measuring a really specific set of things, like things where you need to be able to tell all the different lengths apart. Okay, I can see how that might be useful, but how does this apply to our grid, to those forced points?
Remember how we were saying that every pair of those blue points, those forced blue points, they can potentially cause a problem because they might force a green point that then creates a monochromatic L? Well, if we arrange those blue points on a subdiagonal, like the markings on a glum ruler.
Hold on, I think I see where you're going with this. Because every pair of markings on a golem ruler has a unique distance between them, right? So that means the green points that they force further down, those green points won't be the same distance apart either.
Bingo. It's like a built-in safeguard against creating those troublesome pairs of green points, those pairs that would give us a green L. The glum ruler property prevents that from happening.
That's so clever. But how do we actually, use this? How do we use this to actually get a better handle on R3L? Do we just have to, cross our fingers and hope that the force points happen to arrange themselves like a glom ruler?
No, it's not about luck. It's about using what we know about these rulers, right? We know that for a glom ruler of a given length, there's a maximum number of markings you can have while still making sure all the distances are unique.
Oh, so it's like there's a limit to how many blue points we can safely fit on a subdiagonal before things start to go wrong.
Exactly. And by incorporating this limit, this constraint, into their analysis, right, they could put even tighter restrictions on how those forced points could be arranged. And so, combining this with their interval partitioning techniques, they were able to bring that upper bound all the way down to 772.
7 to 72. Down from 10,593. That's a huge improvement. Those glom rulers, they really did some work. But did they stop there?
Nope, not quite. They kept refining their techniques, refining how they were partitioning those intervals, and using that glom ruler constraint even more cleverly. And they managed to squeeze that bound down even further to 493.
493. Well, it's still a pretty big number, I gotta say.
Yeah.
But I'm starting to really appreciate how much effort, how much ingenuity has gone into, chipping away at this problem. It's really incredible. But we've been so focused on making that upper bound smaller, we haven't really talked much about the lower bound. How do we know that we can't find an even smaller grid size where those monochromatic L shapes just can't exist? How do we know that R3L isn't actually a lot smaller than 493?
That's a great question, and it takes us into a whole different set of techniques. To explore the lower bound, to see if we can make it bigger, the researchers turned to these computational tools called SAT solvers.
SAT solvers.
Yeah.
All right, now this deep dive is taking us from pure math into computer science territory. What are these SAT solvers all about?
They're these incredibly powerful programs that can solve logical problems. So think of it this way, right? The L problem, we can actually encode it as a set of logical rules. We can specify how big the grid is, how many colors we're using, what shape we're trying to avoid, and then we give all of that to the SAT solver, and it tries to find a solution, a way to color the grid that follows all those rules.
So basically we're asking the computer, hey, can you find a way to color this grid without making any of those L shapes that are all one color?
That's it. And if the computer can find a way to do that, right, if it finds a valid coloring, well, that's proof that R3L has to be bigger than that grid size. And get this, they actually used SAT solvers, and they found a valid 3 coloring for a 20 by 20 grid where there were no monochromatic L shapes.
So that means R3L has to be at least 21. That's our lower bound.
Exactly. So now we know R3L is somewhere between 21 and 493, which is that's a pretty impressive improvement, from the initial range we started with.
It is. It really is. But 21 to 493, that's still a pretty big gap, Did they try pushing that lower bound up even further? Did they try using the SAT solvers on bigger grids? I imagine it gets way harder for the computer as the grid size goes up, right?
Oh, yeah, absolutely. They did try to find a valid 3 coloring for a 21 by 21 grid, but so far, no luck. The problem just gets way too complex, way too computationally intensive for even the most powerful computers to handle, at least for now.
So we're hitting the limits of what we can do, even with these super advanced tools.
For the moment, yeah. But that doesn't necessarily mean there isn't a valid coloring out there, a way to color that 21 by 21 grid without any monochromatic Ls. Maybe there's some clever trick, some optimization that we haven't thought of yet that would let those SAT solvers tackle even bigger grids. Or, maybe we need a completely new approach altogether.
Man, it's really exciting to think about. There's still so much we don't know about this problem that seems, at first glance, it's so simple.
That's what makes this kind of research so fascinating, right? Even these really basic mathematical questions can lead us to these deep, unsolved mysteries, and they push us to come up with new tools, new techniques, new ways of thinking.
I know. We've gone from counting pigeons to deep geometric reasoning to diving headfirst into the world of computational logic.
Yeah.
This deep dive has been a wild ride.
It really shows you how connected all these different areas of math are, and, even computer science, too. And for those of you listening out there, those of you who are really grappling with this problem, here's something to think about. Could there be a link between the patterns you see in those colorings that do work, like that 20 by 20 grid, and the strategies that we need to figure out the true value of R3L? Maybe, just maybe, the key to solving that bigger puzzle is hidden within the solutions to the smaller ones.
That's a great question. It really makes you wonder if there's some underlying structure, some fundamental principle we haven't quite grasped yet, something that ties all those different scales together. This has been an incredible journey, and it sounds like the adventure is far from over. To everyone out there who's wrestling with this problem, happy hunting.
Welcome to the deep dive. We're diving deep into Ramsey theory today. Specifically, this L problem on integer grids. I've got a paper here by Mammel, Smith, and Yerger. It's called Ramsey Theory on the Integer Grid, the L problem.
Oh, that's a fun one. It really gets to the heart of Ramsey theory. How certain patterns they kind of have to emerge no matter how you arrange things.
Yeah, it's like you can't hide from certain patterns. It's a mathematical game of hide and seek, but you're destined to be found. So this paper, what's the big question they're trying to answer?
Well, it boils down to this. How big does a grid have to be before you are absolutely guaranteed to find a specific pattern, no matter how you color it? And the pattern in this case is an L shape formed by 3 points. And we're using 3 colors to color the grid.
Okay, and we're looking for that minimum grid size, right? That's what R3L represents.
That's the one. That's the notation for it, yeah.
So for 2 colors, they mentioned it's a 5 by 5 grid.
Right, that's already known.
But 3 colors.
3 colors, things get a lot more interesting, more complicated. And that's where this paper really digs in.
So before we get into all the fancy techniques they use, can we just level set a bit, remind everyone what we mean by an integer grid and a monochromatic L?
Sure. Imagine your typical graph, X and Y coordinates, but we only care about the points where both the X and the Y are whole numbers, integers. So it's like a grid, evenly spaced points. And the L we're looking for it's 3 of these points that form a right angle, like the corner of a square. And monochromatic just means all 3 points of the L have to be the same color.
So we're coloring a giant checkerboard with 3 colors, and we're trying to avoid making an L where all 3 points are the same color.
Exactly.
You can see how that could get tricky very quickly. So the paper starts by looking back at a proof from Kanaki and some others that had an upper bound of 2593 for R3L. Can you remind us how they got to that number in the first place?
Yeah, they use this idea of forced points. Imagine you have 2 red points, but they're specifically on the main diagonal of your grid.
Okay.
Now look at any point below that diagonal. One that could make an L shape with those 2 red points, right? To avoid making a red L, that point has to be either blue or green. It's forced to be one of those other 2 colors.
So you're creating these zones where certain colors are just off limits because of where those initial red points are. It's like a chain reaction kind of.
Exactly. And the more red points you place, you create more and more of these force points. And Kanaki and the others prove that if your grid is bigger than 2593 by 2593, you just run out of room. You can't fit any more forced points without accidentally making a blue or green L somewhere.
That's so cool. It's like a weird Tetris game where you're trying not to complete the pattern.
Yeah.
But this paper, they didn't just stop there, right? They introduced this technique of using intervals on the diagonal to make that bound even smaller. What's that all about?
Right. So instead of looking at individual points, they started thinking about the spaces between red points on the main diagonal.
Okay.
And an interval is just the number of points between 2 consecutive red points on that diagonal.
So if you have two red points right next to each other, that interval length is 0?
Exactly 0. If there's 1 point between them, interval of 1, and so on.
Okay.
And what they figured out is that if you have too many short intervals, it forces you to create a monochromatic L somewhere.
Because those forced points are all crammed together.
Exactly. It gets too crowded. So they have this variable B, which is like the critical threshold for the number of blue points you can have on a subdiagonal. If you have B or more blue points on a subdiagonal, you're going to get that L.
Hold on, before we go any further, can you just remind us what a subdiagonal is in this context?
Oh, sure. It's a diagonal line of points, but it's parallel to that main diagonal, just shifted up or down by some number of rows.
Got it. So, okay, so if a subdiagonal has B or more blue points, boom, monochromatic L. How do the intervals on the main diagonal, how do they tie into this B value?
Each interval on the main diagonal, it creates kind of a shadow of forced blue or green points on the subdiagonals below it. Longer interval, more spread out those forced points are.
So shorter intervals mean more clusters of forced points, more likely to hit that B limit.
Exactly. And their strategy is to try and minimize the total space taken up by those intervals on the diagonal. They start by assuming the smallest number of red points possible.
Okay.
Which also minimizes the number of intervals.
Right.
Then they figure out how to arrange those intervals as compactly as possible.
Like a game of Tetris almost.
Right, yeah, kind of.
Yeah.
And they calculate the absolute minimum space these perfectly arranged intervals would need. They call that SMIN. And here's the kicker. For NGAL 1804, that minimum space, SMIN, it's actually bigger than the length of the diagonal itself.
Wait, so they're saying if your grid is 1804 by 1804, there's physically not enough room on the diagonal to fit all those intervals without forcing a monochromatic L.
Exactly. That's why 1804 becomes the new upper bound. It's the smallest grid size where their whole interval packing thing breaks down.
That's so clever. They shaved, what, over 700 off that initial upper bound just by analyzing those intervals.
Yep. It's all about finding those hidden relationships.
But of course, they didn't stop there. They then went even further, looking at intervals between points that aren't even next to each other.
You're right, they did. They realized they weren't accounting for all the possible intervals.
So not just the space between, say, the first and second red points, but also the first and third, first and fourth, like that.
Exactly. And they use this notation, A, where J and K are the indices of the two red points that are defining that interval.
So like A14 would be the interval between the first and fourth red points.
Yep. And the length of that interval, AK, it's equal to the sum of all the consecutive intervals between point J and K, plus the number of red points in between.
Let me see if I've got this. So A14, its length would be the sum of A12, A23, and A34, plus the two red points that are in between the first and fourth red points.
Precisely. And this lets them build a new inequality, one that takes into account the total length of all possible intervals, the consecutive ones and the non-consecutive ones, relates that to the total space on the diagonal.
So it's a more complete way of accounting for the space on the diagonal, considering all the different ways you can arrange those intervals.
Exactly. And using this new, more nuanced inequality, they recalculate that minimum space again. And what they find is that for n equals 1573, the minimum space needed to fit all those intervals is, again, it's bigger than the diagonal.
So squeezing that upper bound down even further to 1573, it's incredible how much they're able to accomplish just by digging into those relationships between intervals and how those red points are arranged.
Mm-hmm.
But, and I know I keep saying this, they didn't stop there, right? There's more.
You're right, there is. They have even more techniques, and they bring in some really interesting tools to keep refining that bound.
This is where it gets really interesting. But let's let our listeners catch their breath for a minute. When we come back, we'll dive into those even more powerful techniques and reveal that final upper bound for R3L. Okay, so I'm still trying to wrap my head around all these ways of shrinking that upper bound for R3L.
Yeah.
Like that interval stuff, it's so clever.
It really is. It's finding these hidden connections, right? That's where the real power lies.
Exactly. And now we're about to enter like the realm of Golomb rulers, which seems completely different from coloring grids. How did they even like bridge that gap? What do these special rulers have to do with the L problem?
Well, it's actually one of the most elegant parts of the paper. Remember those forced blue points we were talking about on the subdiagonal?
The ones that have to be blue to avoid making a red L?
Right. They made this brilliant connection. Those blue points, in order to avoid making a blue L, they have to form a Golomb ruler.
Wait, hold on. Golomb rulers. Like those rulers where every distance between the markings is unique. I don't get how those fit into this. How do those relate to points on a grid?
Okay, let's break it down. So imagine you have two pairs of those forced blue points, and they're on a subdiagonal. And the distance between the points in each pair, it's the same.
So like two sets of blue points, same spacing, on a diagonal line.
Exactly. Now, to avoid making a blue L, the points that could complete those L shapes, those are forced to be green, right?
Right. Because if those were blue too, we'd have a blue L. And we're trying to avoid that.
Exactly. But here's the thing, because the distances between our original blue point pairs are the same, those two forced green points, they'd end up right next to each other, which would make a green L.
Oh, I see it now. So if the distances between the blue points aren't unique, we're going to create an L somewhere else, even if we avoid the red ones.
Precisely. So to prevent that, the arrangement of those blue points on the subdiagonal, it has to have this special property.
Yes.
All the distances between them have to be unique, just like a Galam ruler. That's how you avoid those extra L shapes.
That's brilliant. They found this hidden rule, and it's based on a concept from like a completely different area of math.
Right. It's amazing how these things connect sometimes.
So how do they actually use this Galam ruler thing to make the upper bound even smaller? I'm guessing there's some clever substitution involved.
You're on the right track. They replaced that general B value, the one that represented the maximum number of blue points on a subdiagonal. They replace it with a more specific value, BK.
And that BK is tied to Galam rulers, right?
Exactly. It represents the largest possible order of a Galam ruler that can fit on a subdiagonal of a certain length. And remember, the order of a Galam ruler, that's just how many markings it has.
Okay, so instead of saying no more than B blue points, they're saying no more than B blue points, where BK is limited by what Galam rulers allow.
Exactly. It's a tighter constraint, and when they plug this more refined BK into their inequality, they find something amazing. For n apparens 493, the conditions for avoiding a monochromatic L, they just can't be met anymore.
So 493 becomes their final, like their best upper bound. They went from 2593 all the way down to 493 just by constantly refining their analysis. It's incredible.
Yeah, it's a really impressive result, but it's important to remember the story doesn't end there. There's still this gap, right, between the lower bound, which is 21, and this new upper bound of 493.
Yeah, the exact value of R3L is still a mystery. So what else did they try? They mentioned using computer programs called SAT solvers to investigate the lower bound. Can you explain what those are and what they found?
Yeah, so SAT solvers are really powerful tools. They're used to solve problems where you have to search through tons and tons of possibilities. Basically, they're algorithms that try to figure out if a certain logical formula can be satisfied.
Satisfied. Like, what does that even mean in this context?
It means, can you assign values to the variables in the formula to make the whole thing true?
Okay. So how do you translate, like, coloring a grid into a logical formula? That seems like a stretch.
It's actually pretty clever. They create a variable for each point on the grid, and each variable, it can be one of three values representing the three colors.
But like if the variable is true, that point is red or something like that.
Yeah, exactly. And then they create these things called clauses, which are basically statements that enforce the rules of the problem. Like one clause might say, if point 101 is red and point 2 and 2 is red, then point 1 and 2 cannot be red.
Right, because that would be a red L.
Exactly. And they build up this whole system of clauses that basically encode all the possible ways you could make a monochromatic L, and then they feed that whole system into the SAT solver.
And the SAT solver, its job is to try to find a way to color the grid, to assign colors to all those variables that satisfies all the clauses at the same time.
Exactly. If it can find a solution, that means there's a way to color the grid without any monochromatic Ls. If it can't, well, that means for that size grid, you're always going to get an L.
So it's brute force, but in a smart way. So what did they find? Did they manage to push that lower bound of 21 any higher?
Unfortunately, no, they didn't improve the lower bound, but they did make some interesting observations about the grids that did work, the ones where they could avoid the L.
Oh, what kind of observations?
They noticed that in a lot of the successful 20 by 20 grids, the colors tend to cluster along these reverse diagonals.
Reverse diagonals. So not the main diagonal from top left to bottom right, but the ones going the other way.
Yeah, exactly. They saw these streaks of the same color along those lines.
Interesting. It's like there's some preferred arrangement that helps avoid the L shapes. Did they look into that any further?
They did, and this is where they brought in another fascinating area of math. Van der Waals numbers?
All right, so we've been talking about this L problem, all the different ways to shrink that upper bound for R3L, And now it seems like we're moving into this whole other area with these reverse diagonal patterns and van der Waals numbers. It's a lot to keep track of.
It is, but it all ties together in a really fascinating way. Remember those successful 20 by 20 grids we were looking at? The ones where they could avoid creating a monochromatic L?
Yeah, they often had those clusters of colors along those reverse diagonals.
Right, exactly. And that clustering, it suggests that there might be something special about those arrangements. Like maybe arranging the colors that way makes it inherently harder to form those Ls.
So it's not just random that those patterns show up. It's like they're somehow connected to the properties of L-free grids.
That's what we're exploring. And to do that, we need to dive a bit deeper into those van der Waals numbers. Remember how those work?
Vaguely. Something about arithmetic progressions and colored sequences.
Right. So van der Waals numbers come from this theorem, and it basically says, if you color a long enough sequence of numbers using a fixed number of colors, you're guaranteed to find an arithmetic progression of a certain length where all the numbers have the same color.
Okay, like if I'm coloring the numbers from 1 to 100 using red and blue, no matter what I do, I'll end up with a sequence like 10, 20, 30, all the same color.
Exactly. That's an arithmetic progression of length 3. And the van der Waals number for 2 colors and a progression length of 3, that tells you the shortest sequence where you're guaranteed to have that happen.
Okay, starting to come back to me.
Okay.
But how do we get from arithmetic progressions to these diagonal lines on our grid?
Well, the author suggests this really clever way to map those reverse diagonals onto number sequences. Think about it. If you move along a reverse diagonal from bottom left to top right, you hit a sequence of points, each one with a color.
So you're turning like a spatial pattern on the grid into a linear sequence of colors.
Exactly. And their idea is that those color clusters we see, they might actually be related to the properties of van der Waals numbers.
So are they saying that the way the colors are arranged on those diagonals, it could be related to these arithmetic progressions that somehow avoid making L shapes?
That's a really interesting question, and one they leave open for future research. But it does hint at a deeper connection between the arrangement of colors on the grid and these van der Waals numbers.
It's amazing how this seemingly simple problem, just coloring a grid, leads to all these complex areas of math, intervals, forced points, Golomb rulers, and now van der Waals numbers. It's mind-blowing.
It really shows how interconnected math is, right? You start pulling on one thread, and it leads you to all these unexpected places.
So where do we go from here? What else did the author suggest we look into?
They left a few really intriguing open questions. For example, can their interval techniques be refined even further?
Yeah, like are there optimal ways to arrange those intervals to minimize the chances of getting those L's?
Exactly. And are there other patterns on the grid, other diagonals maybe, that we haven't even considered yet that might hold some clues?
It feels like we've just scratched the surface of this problem.
We have. That's the beauty of it. The search for a definitive answer to the L problem, it's far from over. And who knows what other tools and techniques might be brought to bear on it.
Well, I, for one, am completely hooked. This whole deep dive has been incredible. From those basic definitions of grids and L shapes to intervals and force points to Golomb rulers, and now these van der Waals numbers. It's been a wild ride.
It has. It's been a pleasure exploring these ideas with you.
Likewise. And to everyone listening, thanks for joining us on this deep dive into the L problem. We'll see you next time for another fascinating journey into the world of math. Welcome to the deep dive. Today, we're going to be taking a deep dive into the world of Ramsey theory.
Oh, cool.
Specifically, we'll be looking at a problem that has puzzled mathematicians for decades.
Okay.
The L problem.
Great.
So imagine a grid, like a checkerboard,
Okay.
where we start coloring the squares using 3 different colors.
Sure.
The L problem asks a deceptively simple question.
Okay.
How big does this grid need to be before we're absolutely guaranteed to find an L shape formed by 3 squares,
Right.
all the same color?
Okay.
Our exploration today is guided by a research paper authored by Mammel, Smith, and Yerger.
Okay.
These mathematicians have used some ingenious techniques, including something called
Interesting.
Golomb rulers, in their attempt to solve this puzzle.
It is indeed fascinating how such a simple setup can lead to such deep mathematical questions.
Right.
The L problem is a classic example of a problem in Ramsey theory, a field of mathematics that studies the conditions under which order must inevitably appear within seemingly random structures.
Okay, so let's dive into the specifics.
Sure.
The paper we're looking at focuses on what's denoted as R3L,
Okay.
the smallest grid size that guarantees a monochromatic L when using 3 colors.
Right.
Now, it's important to note that while it's already been proven that a 2-colored grid only needs to be 5 by 5 to guarantee an L, introducing a 3rd color drastically increases the complexity.
The jump in complexity is significant.
Yeah.
With 2 colors, the problem is relatively straightforward to analyze.
Sure.
But with 3 colors, the number of possible configurations explodes,
Yeah,
making it much harder to establish definitive bounds.
that makes sense.
Yeah.
Now, the paper begins by revisiting a previous proof that established an upper bound of 2593 for R3L.
Okay.
Can you walk us through the logic of that proof?
Certainly. The original proof relies heavily on the pigeonhole principle,
Right.
a fundamental concept in combinatorics. In essence, the pigeonhole principle states that if you have more pigeons than pigeonholes,
Yeah.
at least one pigeonhole must contain more than one pigeon.
Okay, I remember that principle, but how does it apply to our grid problem?
Imagine the points on our grid as the pigeons,
Okay,
and the 3 colors, red, blue, and green, as the pigeonholes.
got it.
The proof starts by focusing on the main diagonal of an nxn grid.
Okay.
Since there are n points on the diagonal and only 3 colors,
Yeah,
the pigeonhole principle tells us that at least n3 of those points must be the same color.
right.
Let's assume, without loss of generality, that those points are red.
So we've got a cluster of red points along the diagonal.
Yes.
What's the next step?
The next step is where things get clever.
Okay.
Look at any pair of those red points on the diagonal. There's a unique point below the diagonal that, if it were also red,
Right.
would form a monochromatic L with those 2 red points.
I see. It's like those 2 red points on the diagonal form the top and corner of the L. And this 3rd point below would complete the shape.
Precisely. And because we're trying to avoid making a monochromatic L,
Yeah.
that point below the diagonal cannot be red.
Right.
It has to be either blue or green.
That makes sense. So for every pair of red points on the diagonal,
Yeah.
we force one point below the diagonal to be either blue or green.
Exactly. And because we have at least n3 red points on the diagonal,
Yeah.
we end up with n3 choose 2, which is nn3, 18 points below the diagonal that are forced to be either blue or green.
Okay, I'm following the logic. So now we have these forced blue and green points below the diagonal.
Yes.
How do we proceed from there?
Now we turn our attention to the subdiagonals.
Okay.
The lines that run parallel to the main diagonal but below it.
Right.
There are n1 subdiagonals in an nxn grid.
Okay.
Since we have nn3 18 blue or green points
Yeah.
and n1 subdiagonals,
Right.
the pigeonhole principle tells us that at least one subdiagonal must contain at least nn3 18 n1,
Cool.
which equals nn3 18 n1 points that are either blue or green.
It's the pigeonhole principle at work. Again, narrowing down our focus.
Exactly.
So we've zeroed in on a subdiagonal that's dense with blue and green points.
Yes.
What's the next move?
We apply a pigeonhole principle one more time.
Okay.
Since the points on the chosen subdiagonal can only be blue or green, at least half of them must be the same color.
Okay.
Let's assume they're mostly blue.
Uh-huh.
Now, each pair of blue points on this subdiagonal will force a point further down in the grid to be green.
Okay.
This is to avoid forming a blue L.
Got it.
Moreover, that green point cannot be red,
Right.
because then it would form a red L with the original pair of red points on the main diagonal that forced this point to be blue or green in the first place.
I'm starting to see how these constraints cascade through the grid.
Yeah.
Each forced point creates new limitations on the coloring of other points.
Exactly. And as we force more and more points to be a specific color,
Yeah.
we're getting closer to the point where it becomes impossible to avoid creating a monochromatic L.
So how does all of this lead to the upper bound of 2593?
The idea is that if n is large enough,
Okay.
the number of forced green points will exceed the available spots on the remaining subdiagonals, inevitably leading to a green L.
Right.
Through calculations using this line of reasoning,
Yeah.
the original proof established that 2593 is large enough to guarantee a monochromatic L in a 3-colored grid.
So 2593 serves as an upper bound, meaning that any grid larger than that will definitely have a monochromatic L.
That's correct.
But, as you mentioned earlier, the paper we're discussing explores ways to tighten that bound.
Yes.
What's their approach?
Mammel, Smith, and Yerger introduced the concept of intervals on the main diagonal to refine the analysis.
Okay.
These intervals represent the distances between the red points we discussed earlier.
So we're looking at the spaces between those red points on the diagonal.
Yes, and the key insight is that the lengths of these intervals directly influence the positioning of the forced blue and green points below the diagonal.
Okay.
Short intervals between red points force blue or green points on nearby subdiagonals,
Got it.
while longer intervals force them further down.
So the intervals provide a sort of blueprint for where those forced points must lie.
Precisely, and by meticulously analyzing the intervals,
Okay.
both those between consecutive red points
Right.
and those skipping over some red points,
Okay.
they're able to deduce a more precise picture of the forced color distribution across the grid.
This sounds like a very detailed and meticulous process.
It is.
How do they actually use this interval information to improve the upper bound?
It's a clever interplay between combinatorics and careful case analysis. Remember, the original proof relied on the pigeonhole principle to demonstrate that if the grid is large enough, we're bound to get a monochromatic L.
Right.
Mammel, Smith, and Yerger take this idea further
Okay.
by meticulously examining the implications of different interval configurations on the diagonal.
Okay, so they're looking at the specific arrangement of those red points on the diagonal and how that arrangement dictates the placement of the forced blue and green points.
Exactly. For instance, they consider scenarios where you might have several consecutive red points on the diagonal, forming an interval of length 0.
Right.
This forces a blue or green point directly below on the subdiagonal.
Okay.
Then they might have a longer interval, forcing points further down.
Yeah.
By carefully analyzing all these possible interval combinations,
Okay.
they can deduce much tighter constraints on the color distribution.
It's like they're playing a game of strategic placement, trying to arrange the colors in a way that avoids creating a monochromatic L for as long as possible.
That's a great analogy. And by pushing this strategy to its limits,
Yeah.
by carefully considering all the possible interval configurations and their consequences, they managed to lower the upper bound from 2593 all the way down to 1573.
That's a significant improvement.
Yeah.
So the intervals play a crucial role in refining the upper bound.
They do.
But you mentioned earlier that they also bring in something called Golomb rulers.
Right.
What are those and how do they fit into this picture?
Golomb rulers are a fascinating mathematical concept that surprisingly finds application in this problem.
Okay.
A Golomb ruler is a set of marks at integer positions along a ruler such that no two pairs of marks are the same distance apart.
So it's like a ruler with very specific, unique markings.
Yes.
How does this relate to the L problem?
Recall that in our earlier analysis, we had a subdiagonal with a high concentration of blue points.
Right.
And each pair of these blue points forced a green point further down to avoid forming a blue L.
Yes.
Now, a key insight is that if any two pairs of blue points on that subdiagonal were the same distance apart, we would inevitably end up with two forced green points on another subdiagonal below.
Right.
That would in turn force a green L,
Got it.
a situation we're trying to avoid.
Ah, I see. So the distances between those blue points on the subdiagonal must all be unique to prevent that from happening.
Precisely, and that's where the connection to Golomb rulers comes in. The arrangement of those forced blue points must form a Golomb ruler to avoid creating a monochromatic L further down the grid.
That's a really clever connection. So by incorporating the properties of Golomb rulers into their analysis,
Yes.
are they able to further improve the upper bound?
They are. By considering the constraints imposed by Golomb rulers,
Okay.
Mammel, Smith, and Yerger managed to push the upper bound down even further
Okay.
from 1573 to an impressive 772.
Wow. That's a remarkable reduction.
It is.
It seems like those Golomb rulers are quite powerful tools in this context.
They are, especially when combined with the insights derived from the interval analysis. And you know what's even more impressive?
That's that.
They were able to refine their techniques further, making some subtle adjustments to their logic, and achieve a final, astonishing upper bound for R3L of just 493.
That's less than half of the previous bound. It's amazing how much progress they were able to make using these seemingly disparate mathematical concepts.
It's a testament to the power of creative mathematical thinking. By combining insights from different areas of mathematics and meticulously analyzing the problem's structure, they were able to achieve a significant breakthrough.
Okay, so we've spent quite a bit of time discussing the upper bound for R3L.
Right.
The maximum size a grid can be before a monochromatic L is guaranteed. But what about the other side of the coin?
Yeah.
How do we explore the lower bound
Okay.
The smallest grid size where it's still possible to avoid creating a monochromatic L.
That's where things get even more challenging computationally speaking.
Okay.
While establishing an upper bound involves proving that a monochromatic L must exist,
Right.
finding a lower bound involves demonstrating that it's possible to color the grid in a way that avoids creating a monochromatic L,
Yeah.
at least up to a certain grid size.
So it's like a game of hide and seek trying to find a coloring pattern that successfully evades those monochromatic L shapes.
Yes.
How do mathematicians even begin to approach that?
That's where we turn to the computational power of SAT solvers.
Okay.
These are algorithms designed to determine whether a given logical formula can be satisfied,
Right.
whether there exists a set of values for the variables that makes the formula true.
Okay. I have a vague understanding of what SAT solvers are. But how do they apply to the L problem?
Okay.
How do you even translate this geometric problem of coloring squares on a grid into a logical formula?
It's a clever process of encoding the rules of the problem into the language of propositional logic.
Okay.
Essentially, we represent each point on the grid as a set of Boolean variables,
Right.
each variable corresponding to a specific color.
So for example, if we have a 10 by 10 grid and 3 colors,
Yes,
each point on the grid would be represented by 3 Boolean variables.
that's right.
One for red, one for blue, and one for green.
Exactly. And then we construct logical clauses that encapsulate the rules of the game.
Okay.
For example, we'd have clauses that ensure each point is assigned exactly one color. We'd also have clauses that prevent the formation of monochromatic L shapes.
Okay.
By stating that if 2 points forming the top and corner of an L are a certain color,
Yeah.
the third point completing the L cannot be that same color.
So we're essentially translating the visual patterns of the L problem into a set of logical statements, a
Exactly.
language that the SAT solver can understand and work with.
Precisely. And the beauty of this approach is that SAT solvers are incredibly powerful algorithms,
Yeah.
capable of sifting through millions, even billions of possible truth assignments to those variables,
Wow.
searching for a solution that satisfies all the clauses,
Right.
meaning all the rules of the game are upheld.
So if the SAT solver finds a solution,
Yes.
a set of truth values that satisfies all the clauses,
Right.
what does that tell us?
It tells us that for that specific grid size, there exists a coloring that avoids creating a monochromatic L.
Okay.
Therefore, that grid size cannot be a lower bound for R3L.
So to find a potential lower bound, we need to keep shrinking the grid size until the SAT solver can no longer find a solution, right?
Exactly. When the SAT solver exhausts all possible truth assignments without finding a solution that satisfies all the clauses, it means there is no possible way to color a grid of that size without creating a monochromatic L.
Okay.
That grid size then becomes a candidate for the lower bound.
But it's not a definitive proof, right?
That's correct.
The SAT solver just provides strong evidence.
That's right. The SAT solver gives us a strong indication,
Yeah.
but mathematicians still need to come up with a rigorous mathematical proof to definitively establish the lower bound.
It's fascinating how this process involves a dance between computational exploration and rigorous mathematical proof.
Yes.
The SAT solver is like a scout venturing into the vast wilderness of possibilities and reporting back on what it finds.
Yeah.
But ultimately, it's the mathematicians who have to carefully map that territory and establish the boundaries with certainty.
It's a powerful synergy between computational power and human ingenuity. Now let's delve into some of the specific strategies that researchers use to make these SAT solvers more efficient.
Okay.
Because, as you pointed out, even with their impressive capabilities, these problems can quickly become computationally intractable as the grid size increases.
Yeah, I can imagine that even supercomputers would struggle to handle the sheer number of possibilities involved as the grid gets larger.
They would.
So what tricks do mathematicians have up their sleeves to make this process more manageable?
One common strategy is to break down the problem into smaller, more manageable chunks.
Okay.
Instead of tackling the entire grid at once, researchers might instruct the SAT solver to focus on specific sections of the grid,
Okay.
like triangular portions.
It's like solving a giant jigsaw puzzle by focusing on assembling individual sections first.
Exactly. And by strategically dividing the grid into smaller regions,
Yeah.
they significantly reduce the number of variables and clauses that the SAT solver has to contend with at any given time, making the computation much more efficient.
It's a clever approach. Are there any other techniques they use to guide the SAT solver's search?
Another powerful technique is to fix the colors of certain points on the grid beforehand.
Okay.
For example, they might instruct the SAT solver to assume that the top left corner is red and the bottom right corner is blue.
Okay.
And then explore whether a valid coloring exists under those constraints.
It's like giving the SAT solver some hints to narrow down its search base.
Precisely. By strategically fixing the colors of certain key points,
Right.
researchers can dramatically reduce the number of possibilities the SAT solver has to consider,
Yeah.
making the search for a solution much faster.
Okay, so we've got these techniques of breaking down the grid into smaller sections.
Yes.
And fixing the colors of certain points to help streamline the SAT solver's process.
Mm-hmm.
Are there any other tricks of the trade that researchers employ?
Yes, there's another interesting technique that leverages the inherent symmetry of the grid. Instead of treating each point on the grid as unique,
Yeah.
researchers can exploit the fact that the grid has rotational and reflectional symmetry.
I'm not sure I follow. How do they incorporate symmetry into the SAT solving process?
Imagine you rotate the grid by 90 degrees,
Okay.
or you flip it along a diagonal.
Right.
The underlying problem remains the same, right?
Yeah.
The L problem is invariant under these transformations.
That's true. The relative positions of the points and the shapes they form don't change.
Right.
Just their orientation within the grid.
Exactly. So researchers can leverage this symmetry to reduce the number of variables they need to consider.
Okay.
Instead of having a unique set of variables for every single point on the grid,
Right.
they can group together points that are equivalent under rotation or reflection and represent them with the same set of variables.
That's a really neat trick. It's like they're folding the grid onto itself, collapsing those symmetric points into a single representative.
Precisely. And this symmetry reduction can significantly shrink the size of the logical formula that the SAT solver needs to process,
Yeah.
making the computation much more efficient.
So it's a combination of clever problem decomposition, strategic hints, and exploiting symmetry that allows researchers to harness the power of SAT solvers to explore these computationally challenging lower bounds.
Exactly. It's a beautiful example of how human ingenuity and computational power can work together to push the boundaries of mathematical knowledge.
It's truly impressive how these seemingly simple questions about coloring squares on a grid can lead to such deep and sophisticated mathematical explorations.
And that's just the tip of the iceberg. As we delve deeper into the world of Ramsey theory on the integer grid, we encounter even more fascinating questions and surprising connections to other areas of mathematics.
Speaking of surprising connections you mentioned earlier, the researchers noticed something intriguing about what they called reverse diagonals on the grid.
I did.
Can you elaborate on that? What's so special about these reverse diagonals?
Certainly. Reverse diagonals, as their name suggests, run from the bottom left corner of the grid to the top right corner,
Right.
opposite to the direction of the main diagonal. What the researchers observed was a curious tendency for colors to cluster along these reverse diagonals in many of the colorings they explored.
So it's like those reverse diagonals act as magnets attracting points of the same color.
That's a great way to put it. And this unexpected clustering behavior led them down a path toward another fascinating area of mathematics.
Oh,
Van der Waals numbers.
Okay, now you've really piqued my curiosity.
Yeah.
I've heard of van der Waals numbers in passing,
Mm-hmm.
but I'm not quite sure what they are or how they relate to our grid coloring problem.
Okay.
Can you shed some light on that connection?
Absolutely. Van der Waals numbers are a concept from Ramsey theory that deals with arithmetic progressions. An arithmetic progression is a sequence of numbers where the difference between consecutive terms is constant.
Like 2, 5, 8, 11, where the common difference is 3.
Precisely. And van der Waals theorem states that for any given number of colors and any given length of arithmetic progression, there exists a number n such that if you color the integers from 1 to n with those colors, you're guaranteed to find a monochromatic arithmetic progression of that given length.
Okay, I'm following so far.
Yeah.
We've got arithmetic progressions and this guarantee of finding monochromatic ones if we color along in a sequence. But how does this relate back to the L problem and those reverse diagonals?
The key insight is that each reverse diagonal on the grid can be viewed as a potential monochromatic arithmetic progression.
I'm not sure I see that connection.
No.
How can a diagonal line be an arithmetic progression?
Consider a single reverse diagonal, and let's say it's mostly blue. If you look at the column numbers of the blue points along that diagonal, you'll notice that they form an arithmetic progression.
Can you give an example?
Sure. Let's say the first blue point on that diagonal is in column 3. The next blue point might be in column 6, then column 9, and so on. The column numbers are increasing by a constant amount, 3, in this case forming an arithmetic progression.
Ah, I see it now. The column numbers of those blue points indeed form an arithmetic progression.
Exactly. And because all those points on the diagonal are the same color blue in our example, we can consider that entire reverse diagonal as a monochromatic arithmetic progression.
So each reverse diagonal on the grid can be viewed as a potential monochromatic arithmetic progression. And that's where the connection to van der Waals numbers comes in.
Precisely. By connecting those reverse diagonals to arithmetic progressions, the researchers could tap into the insights provided by van der Waals theorem to gain a deeper understanding of the L problem. It's like they found a hidden bridge between these two seemingly disparate areas of mathematics, a bridge that allows them to leverage knowledge from one domain to shed light on another.
This is absolutely fascinating. It's incredible how even a problem as seemingly straightforward as coloring squares on a grid can lead to such deep and unexpected connections across different mathematical concepts.
It really highlights the interconnected nature of mathematics, how seemingly unrelated concepts can converge in unexpected and beautiful ways. Now, given that we've established this fascinating link between the L problem and van der Waals numbers, how did the researchers actually utilize this connection in their exploration of the lower bound?
Yeah, that's a great question.
They used it to gain insights into the structural properties of colorings that successfully avoid monochromatic Ls. Remember, van der Waals theorem guarantees the existence of monochromatic arithmetic progressions in sufficiently long sequences. By relating the reverse diagonals to these arithmetic progressions, the researchers could start to reason about how the color distribution along these diagonals might influence the emergence or avoidance of monochromatic Ls.
So they weren't using van der Waals numbers to directly compute the lower bound, but rather to understand the underlying patterns and constraints that govern the L problem.
Exactly. The connection to van der Waals numbers provided a new lens through which to view the problem, a new set of theoretical tools to help guide their exploration.
This is really remarkable. It's like they're weaving together threads from different branches of mathematics to create a richer tapestry of understanding.
That's a beautiful way to put it. And as they continue to explore these connections, who knows what other surprising and elegant patterns they might uncover in this seemingly simple problem of coloring squares on a grid?
Now, before we wrap up our deep dive into the L problem, I'd love to touch upon another aspect of their research that we haven't discussed yet, their efforts to improve the efficiency of SAT solvers.
Yeah.
We've talked about techniques like problem decomposition, strategic hints, and symmetry reduction. But did they introduce any novel approaches to enhance the performance of these algorithms?
They did. In addition to those standard techniques, they explored a method known as clause learning, which is a powerful technique used in modern SAT solvers to speed up the state process.
Can you explain how clause learning works in the context of the L problem?
Certainly. The basic idea behind clause learning is to dynamically add new clauses to the logical formula as the SAT solver explores the search space. These new clauses capture information about conflicts or inconsistencies that the solver encounters during its search.
So it's like the solver is learning from its mistakes, identifying patterns that lead to dead ends, and encoding those patterns into new clauses to avoid making the same mistakes again.
Precisely. Let's say the SAT solver is exploring a particular branch of the search tree, assigning colors to points on the grid based on the existing clauses. If it reaches a point where a conflict arises, for example, it assigns a color to a point that would inevitably create a monochromatic L based on previous assignments. The solver analyzes the chain of decisions that led to that conflict.
It's like retracing its steps to figure out where things went wrong.
Exactly. And based on this analysis, it constructs a new clause that encapsulates the essence of that conflict, essentially saying, don't make this combination of assignments again, it will lead to a problem. This new clause is then added to the logical formula guiding the solver's future search and preventing it from wasting time exploring paths that are known to be fruitless.
So by dynamically adding these learned clauses, the SAT solver becomes more intelligent, more efficient in navigating the vast search space. It's like giving the solver a roadmap with markings that say dead end or detour.
That's a great analogy. And this clause learning technique has been instrumental in pushing the limits of what SAT solvers can achieve, enabling researchers to tackle increasingly complex problems, including those in Ramsey Theory, on the integer grid.
This is truly remarkable. It's amazing how these advancements in SAT solving algorithms are opening up new frontiers in mathematical exploration, allowing us to tackle problems that were previously considered computationally intractable.
It's an exciting time to be working in this field, witnessing the interplay between theoretical mathematics and cutting-edge computer science.
As we reach the end of our deep dive into the L problem, I'd like to step back and reflect on the key takeaways from our exploration. What are the most significant insights that we've gained from Mammel-Smith and Yerger's research?
Their work has significantly advanced our understanding of the L problem on several fronts. They've developed powerful techniques such as the interval analysis and the Golomb ruler connection to dramatically reduce the upper bound for R3L, providing a much tighter constraint on the maximum grid size needed to guarantee a monochromatic L.
And their explorations on the lower bound, using sophisticated SAT solver techniques and leveraging connections to van der Waerden numbers, have provided valuable insights into the structure of colorings that successfully avoid monochromatic L shapes.
Precisely. Their research is a beautiful demonstration of the power of combining rigorous mathematical reasoning with computational exploration, a testament to the creativity and ingenuity of mathematicians working at the forefront of this field.
Before we conclude, I'd like to leave our listeners with a final thought to ponder. Throughout this deep dive, we've been focused on the specific shape of the L. But what if we were to generalize this problem? What if we were interested in other shapes, squares, rectangles, T-shapes, or even more complex configurations? How would the bounds change? What new challenges and connections might we encounter?
That's a fantastic question, and it opens up a whole new realm of possibilities within Ramsey theory on the integer grid. By changing the target shape, we're essentially altering the fundamental rules of the game, and this can lead to a cascade of new questions and insights.
It's like we've just scratched the surface of a vast and intricate mathematical landscape.
Absolutely. And who knows what hidden patterns and surprising connections lie waiting to be discovered in this colorful world of grids and shapes. It's a reminder that even in a field as seemingly specialized as Ramsey theory, there's always more to explore, more to learn, and more beauty to uncover.
And on that note, we'll leave you, our intrepid listeners, to ponder those possibilities. Until next time, keep exploring, keep questioning, and keep diving deep into the wonders of the mathematical universe.